When we developed quantum mechanics in the 1930s, it is human beings using these ideas that is responsible for the bomb and for using the bomb. And Albert Einstein famously said, there are only two things in the universe that might be infinite: space and human stupidity. And he said he wasn't sure about space, right? And so these tools need to be used in a manner that ultimately benefits all humankind. We believe that the universe has a fundamental element of chance, a fundamental evolution that is governed by probabilistic laws, a statistical description of how the universe actually works. And if the experiments are showing you that the micro world does not behave like the macro world, you have to take these ideas seriously. The fact that you all have all manner of technology that makes use of the integrated circuit, none of that would exist were it not for quantum physics. It is only by using the quantum mechanical laws that we are able to harness the motion of these electrons, and in that way to create these microscopic circuits that have transformed the world. Good afternoon, everyone. First, I just want to thank the organizers of this conference, the founders of this conference. This is my first time in India. The hospitality was absolutely amazing. It's been a wonderful trip, so thank you so much. I'm going to be talking about the next things in physics, and the next things are already upon us. The next things have to do with the arena of quantum physics, quantum mechanics. And in order to push the frontiers of our understanding and the technological applications, it's vital that we all have at least a basic understanding of what the new ideas of quantum physics are all about. So toward that end, I'd like to give you a sense of what we have found in the last 100 years of quantum physics, and then a sense of where we might be going in the future. And to do that, let me contrast quantum physics with what we typically call classical physics. Classical physics, that's a physics that really came to us from Isaac Newton in the late 1700s, late 1600s, and so on, had been developed. It's the physics that we teach to students around the world today. And the beautiful thing about classical physics is that we all have classical physics in our bones, in our intuition, right? I mean, you take any ordinary object, and if I toss it like this, nobody is impressed. And the reason why you're not impressed, because all of us can do this. But this is an amazing achievement if you think about it, because the motion of this object and the motion of my hand to be in exactly the right position to catch this object, that's a very complicated process. But we all can do it. Animals can do it. My dog can do it. And the reason for that is we have brains that evolved over the course of thousands of generations in order that we could survive. And to survive, you need to understand how the physical universe works. And that's why we have this capacity to understand classical physics intuitively in our bones. But imagine that you consider a realm of reality that we have never directly experienced. Imagine diving into the structure of matter and going orders of magnitude smaller and smaller and smaller until you reach the scales of molecules and atoms. We are down to the scale of 10 to the minus 10 to 10 to the minus 15 meters, distant scales that none of us have ever directly experienced. So you might imagine that the physics that we understand in the everyday world simply does not apply in the microscopic world, and that's exactly what was discovered during the last 100 years. In the early years of the 20th century, a new physics emerged from the micro world, and that is quantum mechanics. And I just want to give you the key ideas of what quantum mechanics tells us. And to do that, let me contrast it a little bit more specifically with how the world behaves on everyday scales. So imagine you're watching two people play a little game of baseball, American cricket, if you will. And imagine that you have a pitcher who is able to throw the ball toward the batter and throw that ball in exactly the same way on every single toss. And imagine, too, that the batter has the capacity to swing that bat in exactly the same way on every try. Now, what we know is if you throw the ball the same way and the batter hits the ball the same way, then the ball will always land in the same location. Same conditions, same laws, yield same outcome. This is the critical part of science as we experience it. Regularity, a pattern, something that is repeatable. And indeed, we can encapsulate all that motion of a ball being thrown and a bat hitting that ball. We can encapsulate that in a basic mathematical equation that Isaac Newton first wrote down. That equation is simply F equals ma, an equation that we still teach to high school kids around the world. But the point is, it is repeatable, it is replicable, same conditions, same outcomes. When we began to investigate the micro world, not the everyday world, we found that you could have the exact same conditions, the exact same situation, and yet you would get not the same result. If you had a microscopic version of that little baseball example, where we shrunk down the pitcher, shrunk from ordinary scales down to atomic scales, and we take the batter, and we shrink the batter down from ordinary scales to atomic scales, and they play exactly that same game of baseball, where the pitcher is throwing the ball toward the batter, and the batter is swinging in exactly the same way on every single iteration of the experiment, you do not find that the ball will land in the same location each time. Instead, you find that the ball will land in a whole variety of different locations. There is an element of chance that emerges in the microscopic world. Now, at that point, you might say we need to give up. We can't understand the physical world if it isn't repeatable, replicable. If the same conditions don't yield the same outcome, maybe we should give up. And there were people who suggested that. But the amazing thing is, scientists kept at it, and they found that if you run an experiment over and over again, you get many different outcomes, but there is a pattern. There is a pattern to what you find. You find that the results can be described using the language of probability. In any given experiment down in the microscopic world, you can say, for instance, that the ball, 20% chance it will land here, 30% chance, 50% chance over here. So it is not completely random, it's just a different kind of pattern. In the everyday world, same conditions, same laws, same outcome. In the micro world, same conditions, same law, different outcomes, but the outcomes do have a pattern, a statistical pattern, a probabilistic pattern. And the wonderful thing is, we were able to write down equations to describe those probabilistic outcomes. The year 1925 Werner Heisenberg, a German brilliant physicist who is suffering from some devastating allergies. He leaves the mainland of Europe and goes to the island of Helgoland. And on the island of Helgoland, Werner Heisenberg, thinking about these very ideas, writes down a mathematical equation that he believes describes these probabilities. 1 year later, Erwin Schrödinger, who is suffering a devastating cough, he thinks he may have tuberculosis. He leaves Zurich and he goes to the town of Arosa in the Swiss Alps. And in the Swiss Alps, using the fresh, crisp mountain air as part of his inspiration, Erwin Schrödinger writes down an equation that he believes describes these probabilities. Amazingly, two separate individuals using two separate mathematical languages, they actually write down the same mathematical equation, an equation that we believe takes the place of Newton's equation. And using that equation, we can make predictions for the probabilistic outcomes of quantum experiments. And if the mathematics says that, say, a particle like an electron should be found 20% here, 30% here, and 50% here, if we run an experiment over and over and over again, indeed, 20% of the time we do find it here, 30% we do find it here, and 50% we do find it at this location. And that is why we believe these ideas. We believe that the universe has a fundamental element of chance, a fundamental evolution that is governed by probabilistic laws, a statistical description of how the universe actually works. Albert Einstein resisted this idea, famously saying that he did not believe in these probabilities. He did not believe, as he described it, that God plays dice. Niels Bohr, one of the other founders of quantum physics, got tired of hearing Einstein repeating that God does not play dice. Niels Bohr finally responded and said, "Einstein, stop telling God what to do." What he meant by that is, physics is not in the business of making us feel good. Physics is not in the business of trying to align with our intuition. Physics is in the business of trying to understand the natural world. And if the experiments are showing you that the micro world does not behave like the macro world, then you have to take those experiments seriously. And if the human brain is able, through analysis, to work out the patterns in the micro world and encapsulate them with mathematical equations, as Heisenberg and Schrödinger did, you have to take these ideas seriously. Now, the wonderful thing is, it's not simply a matter of being able to confirm our understanding. People have been able to take these quantum ideas and apply them, yield technological breakthroughs that have transformed our world. For instance, the fact that you all have a cell phone, the fact that you all have a personal computer, the fact that you all have all manner of technology that makes use of the integrated circuit, none of that would exist were it not for quantum physics, because those tiny circuits involve manipulating the motion of little particles like electrons and making them go through tiny, specific circuits to carry out specific processes. If we try to use the ideas of Isaac Newton and apply them to electrons, we would fail in being able to develop these kind of microscopic circuits. It is only by using the quantum mechanical laws that we are able to harness the motion of these electrons, and in that way to create these microscopic circuits that have transformed the world. People have done calculations, I've not done it myself, but something on the order of 30 to 40% of the gross national product of industrialized nations relies upon these breakthroughs of quantum physics. And so these ideas are not only transformative in our thinking, they are not only specific in their predictions for what happens in the micro world, they can be harnessed to do things that have transformed the world as we know it. But what do we make of the new reality? How do we think of the universe in this new language of quantum physics? And for that, I want to turn to what is probably the strangest, the most puzzling, but perhaps the most profound quality of quantum mechanics of all. And that is something that is known as quantum entanglement. Quantum entanglement, it's an idea that emerged from Albert Einstein in the year 1935 as he sought to somehow find a flaw in this quantum description of the world that was not aligning with his intuition. Einstein was struggling to try to have a worldview that would mesh with his understanding of how he thought reality should behave. And so he studied quantum physics and realized the following prediction of the quantum mathematics. And the prediction is this: you can have a particle at one location, say in my right hand, another particle in my left hand, and they can be widely separated. I'm just using my arms as a concrete example. And you can do a measurement on this particle in my right hand, and that measurement can somehow immediately affect the particle in my left hand. It's as if these two particles that are widely separated somehow behave as though they are one. Einstein called this idea spooky. Spooky action at a distance. You do something over here, and it instantaneously affects something over there, regardless of how far apart these particles are. He brought this idea to the leaders of quantum mechanics, and at first they were quite disturbed by this unexpected quality of the quantum world that they had been developing using their mathematical equations. But in the end, they said, well, maybe that is how the universe behaves. We are used to a universe in which if you do something here, it affects things here. Sure, over time, the effect can ripple outward. But if you do something here, you can't immediately affect something far away. We are used to a world where if you are, say, pouring sugar in New York, you can't sweeten somebody's tea in Delhi, right? That's not the universe that we know of. And yet, quantum mechanics was suggesting some kind of long-range influence. When the scientists sat down to devise experiments that could test this idea and ultimately carried out those tests, they found that the universe is indeed non-local. They found that in quantum physics, indeed, the supposed flaw that Einstein illuminated is not a flaw at all. It is a quality of the microscopic world. What you do over here can, in a very strange quantum mechanical way, be connected with something that happens far away. Now, what can you do with this strange, non-local quality of quantum physics? Well, scientists have now been able to leverage this non-local quality to undertake quantum teleportation. Quantum teleportation, what is that? Well, we all know the basic idea, the science fiction idea, the fanciful idea of taking an object at one location and making it rematerialize at another location. I underscore science fiction because most of us do not think that would be possible. And yet, using quantum entanglement, scientists have now been able to take a particle, a single particle, take that particle, have it interact with one member of an entangled pair, say in New York. Through that interaction, the particle can imprint its properties on a particle far away, say in Paris. And then in Paris, there's a protocol that an experimenter can undertake to extract an exact version of the particle that was in New York. They can extract it in Paris. They can teleport the particle from one location to another. Anton Zeilinger, one of the great quantum physicists of our age, and also one of the great leaders in knowing how best to set up a physics laboratory, has a laboratory in the Canary Islands off the coast of Spain. Tenerife is one island, 90 miles away, La Palma. He regularly teleports particles from one island to another island. This is no longer science fiction. This is how the world behaves. Now, of course, the natural next question is, okay, so you can teleport one particle from one location to another. Can you teleport a macroscopic body, a large collection of particles like a person? There is, at the moment, no known way to extend the protocol for teleporting individual particles to large collections of particles. But this, of course, is the first step in that direction. And the only thing that I can say for sure is that if at some point we do have a possible way of teleporting a macroscopic collection of particles from one location to another, I can tell you for sure I will not be the first person that steps into that device. But this is the kind of science fiction sounding idea that is beginning to emerge from the insights into the micro world that have come from quantum physics. But in talking about the next things that these ideas could lead to, of course, it is quantum computing. And this will be the last thing that I will make reference to. Quantum computing, what is it? How do you leverage these ideas to speed up computation? Well, to get to this idea, let me explain one big mystery within quantum mechanics that we still have not resolved. And part of that resolution will inform the way these ideas can be implemented in our technologies of the future. What is that problem? The problem is this. I mentioned that the new idea of quantum mechanics is that you can't predict the definite result of an experiment. You can only predict the probabilities of getting one or another answer still. The probabilities that a particle will be here, there, or over there. The question is, how do you think about that reality? This is a reality in some sense that hovers in a fuzzy mixture of many possibilities, and then when you observe that reality, you get one or the other outcome still. We never see a single particle in multiple locations. When we measure a particle, we always see it in one single location. So the question is, how does the universe evolve, transform from a reality which has this fuzzy mixture of many possibilities to a single definite outcome upon observation, upon measurement? That is the puzzle. One possible solution to that puzzle, which is useful for thinking about quantum computing, is this. When you measure a particle like an electron, which could be here, there, or over here, when you measure it, you only find it in one of those locations, but perhaps what really happens is the universe splits into multiple universes, where one of you finds the particle at this location, another of you finds the particle at this location, and a third version of you finds it at this location. All possibilities actually happen, but they happen to happen not in one universe, they happen in different universes. It's the so-called many worlds interpretation of quantum mechanics. We don't know if it's the right way of thinking about quantum mechanics, but let's go with it for this last point about quantum computing. How does quantum computing speed up classical computing? Well, if quantum mechanics embraces many worlds, many universes, then you can take a given calculation and do part of it in this universe, part of it in this universe, and part of it in this universe. You can speed up the computation because you are leveraging the computational power of many universes to work in parallel to try to extract the answer that you are looking for. Now, obviously, the challenge in quantum computing, if you are imagining breaking up a calculation into something that takes place in different universes, sooner or later, you've got to put it all back together and extract one answer in the universe that you are inhabiting. This is what quantum algorithms do for us. There are only some problems where we have quantum algorithms capable of blending the results from these parallel computations to get the answer that we are looking for. One of the problems that we can do this for is factoring large numbers. Why does that matter? Factoring large numbers is the key to breaking the cryptographic schemes that protect everything that we do online. Protecting your bank account, your passwords, everything that you care about, everything that you do not want to be in the hands of somebody else is protected through these kinds of cryptographic schemes. Quantum computing has the capacity of breaking those cryptographic schemes. Now, that is potentially frightening. So what we need to do, of course, you need to have enough of these computational structures in the hands of so-called the good actors to keep one step ahead of these computational schemes that are being developed by the bad actors. And so it is vital as we go forward to be cognizant that science is a tool, right? Science is value neutral in terms of what it does, right? I mean, when we developed quantum mechanics in the 1930s, one of the applications in the 1940s was the atomic bomb, right? It's not that quantum mechanics inevitably led to the bomb. Quantum mechanics is not responsible for the bomb. It is human beings using these ideas that is responsible for the bomb and for using the bomb. And Albert Einstein famously said, there are only two things in the universe that might be infinite: space and human stupidity. And he said he wasn't sure about space, right? And so these tools need to be used in a manner that ultimately benefits all humankind. And so we've got powerful technology that is on the horizon, leveraging these ideas of quantum physics to undertake calculations that otherwise would be impossible to ever complete. And that power is something that we need to have great respect for. We need to understand it, and we need to ensure that we use it in ways that ultimately benefit us all. And this is merely one application of the ideas of quantum physics. I imagine if we have another next conference 25 or 50 years from now, and if I am fortunate enough to still be here and fortunate enough to still be relevant enough to be invited back, it is exciting to imagine what those applications of quantum physics might be. Thank you very much.